Hi, my name is Hirani. This is a Simulink tutorial that I'm doing for Yellow Jacket Space Program. Okay, so why should we learn simulation? Simulation is a tool that allows us to visualize mathematical models. But you can say that these models already exist. Why do we need simulation? Well, math is hard, coding is easier than math. Right now, so whenever you have a physical system, a lot of times you're going to have equations up the wazoo where you won't be able to solve everything you need to. However, if you code those using numerical methods and solve them, you can get a rather close approximation of the physical system with a numerical approximation. And this allows you to model and control complex dynamical systems and quickly evaluate different design choices without fully detailed models or a clear idea of everything that you want in the system. It allows you to vary parameters, etc., without the need for long lead times in your model generation. Today we're going to cover two systems, mechanical simulation using to model the suspension response to abrupt changes in road surface conditions, and finally an electromechanical simulation using Simscape to model the backdriving characteristics of a DC motor and PWM driver. Okay, let's get started. So, to open up Simulink, what you're going to do is you're going to open up MATLAB. Once you've opened up MATLAB, there will be this button over here at the top called Simulink. It's rather hard. Sometimes it's not as easy to see, but it's pretty much dead in the center of your home tab. So tell me when you guys are ready for me to move on. Good. Okay, got it. So, okay, Simulink is open. To create your tools, you open up a blank model. Okay, this is your workspace area. It's a blank screen. Effectively, you put blocks that are called nodes and connect them up using wires. Now, to do the first example and model the suspension kinematics, what we have to do is we first have to derive what is called the equations of motion for the system. So, let's do that. So, when you have a vehicle suspension model, first steps are to draw the... Hold on, this is weird. Okay, so I can't press that button. Okay, so first step, let's draw a car. So, what? Okay, hold on. This is also the first time I've used a Wacom tablet, so. Okay. Okay. We'll deal with it.
It's got wheels.
Okay.
So it looks like a car going at you.
So now, what you do? So your wheels have forces on them. Now, why is that doing that? I don't know. Oh, you can actually move it by being up above it. All right. So your forces include a weight of your vehicle, your friction force, and you have spring forces pushing your vehicle down, and as well as normal force pushing the wheel up. So this is also a very bad model. So here's what you're going to do. You're going to simplify your model. So we're going to choose a mass here with, so this mass will model your vehicle, and then you're going to have a dashpot, and a spring connecting another mass, your wheel, and then let's see. And I'm going to draw that over here. Go back then. And then connected to that wheel, you have another dash pot. A spring, which then connects to the ground. This is your fixed ground. Alright, in order to analyze this, we're going to pick 2 reference points. Your ground and your vehicle motion center. So, alright, I don't think I clearly explained what these are. So this is the mass of your wheel, your unsprung mass. This is your vehicle mass, and then you have your road surface. So variations in your road surface can be modeled by the parameter u0, and then we're going to set two variables as a response variables, x1, x2. Okay, by setting up the differential equations for motion using Newton's second law, you're going to get that m x2 dot is equal to negative b x1 dot. You're going to get a lot of equations that look like this. And what you do, minus x1, and what these equations will tell you is that those are some hairy, you're going to get a hairy system of differential equations. Now to solve that, you have a set of options. So in Simulink, you can pick up, so this is a completed model of this system. So I'm going to explain it in a few steps, and then we're going to create a simpler model of it. So step 1, this is your input area. So what happens is that you have these nodes here, random number, ramp, saturation, etc. To create nodes, you simply go to the library browser and look up the node you want. So let's say you want a integrator. It'll search for it. Normally it doesn't do this. There. Okay. So it'll find you a list of the things you want. You can take the block you want and just drop it into space. Whenever you do that, it'll give you some parameters called block parameters, and you effectively just tell it what you want. And then now you have your integrator block. So some UI interface controls that you might want to know. Your scroll wheel will control zooming in and zooming out. You can pan by middle click. And now these endpoints are considered nodes, or not nodes. these endpoints allow you to connect two different nodes to each other and create and form data loops. So there's three different types. So this is Simulink. So if I show you another block, so another way to add a block is just click in dead space and type. All right. This will give you a constant. Now, you just drop a block in place. If you drop it in line, it'll give you an arrow, and if you click it, it will automatically connect it. Now, as you can see that this one is black. This black line represents data. So data is allowed to be is a one-way path and is only transferred in one direction. So there's no feedback that goes in. This goes back from the integrator to the constant. Conversely, if we look at a physical model, you're going to see lines that are blue and green. Blue lines are electrical circuits. They carry current and are physical simulation lines. And green lines are mechanical simulation lines and move from and contain and transfer data from such as rotational velocity, forces, kinetics, etc. You can transfer I think that Neil disconnected. Yes, he did. So the blue lines connect. So the difference between red, blue, and black red, green, and black lines is that data can be transferred in both directions in these physical simulation lines, whereas black lines only allow for one-way transfer of data. So an example would be inertia is allowed to backdrive the motor in this example. We'll get to that in a second. But once you connect, so if you have a constant, you pass it through an integrator, what do you think you're going to get?
0.
If you integrate a constant.
Oh, you're going to get an x. You're going to get a function.
So you're going to get this is a time-based integrator, so you're going to get a line with a slope of 5, right? Because we set our initial condition to 0. So to see that, there's a block called a scope. This scope, you can specify the number of input ports. Something to know about that is that if you only have one input port, you won't actually be able to change it to have more. So you got to delete the block and add a new one and can reconnect all your lines if you want to increase the number of ports. So if you double click on it, you'll see, oh, why aren't we seeing a line? Because the simulation hasn't been run yet. So in order to run your simulation, you got to either select the run button here or double click this and then click run here. So you can see that you get a 5, yes, okay, that works. So you can see that you get a line of 0 to a line that starts at 0 with a slope of 5. Now, what you could do then is also implement a feedback loop. So let's say that you want a sum. So say you want to take what's here, add this here, and then integrate it again. So what you're going to do, delete this. And now what you're doing is something kind of cool. So you're taking 5 and adding it to the output of an integrator whose initial value is 0, and then you're integrating it. So what do you think you're going to get?
Curve with the just be the area of the previous curve we had, right?
Yeah. That isn't what happened. Okay, so this is an example of feedback characteristic. Actually, this turned into an exponential function. So what we're going to do is new. Okay, there we go. So what we saw was that you had what? No. So you had your 5. Now let's look at this as a step-by-step integration. So this is going to explain to you what numerical methods are in this case. So you start out with 5, and this is step 1. So in step 1, you're going to start out with 5, and it'll go straight, pass through an integrator. It'll go through the sum of an integrator block, which starts at 0, and then it'll be integrated again. So at the end of this, what's passed into the integrator is 5, right? Now, the next step it's going to be passed through is 2. That 5 is held back. An integrator block is simply a block that stops or delays a movement. So what'll happen is that whatever's in that block in the previous iteration is stored, and then it's outputted again in the next iteration. So and multiplied by a really small time constant and added. So if you keep doing that and you keep adding 5, it's effectively multiplying by 5 each time. So that's why we're getting an exponential curve. So feedback can cause stuff like that to happen rather easily because this is a positive feedback loop. Now, you can change the sign and subtract 5 every time, but it doesn't actually do what you think it's going to do. It's not going to try to cancel out the negative feedback. So it's going to tend towards negative infinity instead. This is something that happens a lot when you're trying to debug your models. So let's take a look at this suspension model that we are going to develop. So what we are modeling is a slope. So we're going to try to model the response of a vehicle system going up a 0.05 meter slope, and its slope is 5 centimeters a second, but it stops after getting to 1 centimeter of height. Okay. So let's try to run this simulation, and you're going to see that something's not quite right. So you get a bunch of errors. So what I've done is I've defined parameters for spring rates, damping coefficients, etc. You can do that. You can take models from other stuff, take data that you've already collected from, let's say, experimentation or data collection otherwise, and use that in your Simulink models. So in connecting all of these together, so in order to use that data, you have to go into MATLAB and then simply go to one second to find where this is. So you could either load data into here, or in the command window simply type in some values for all of the components. So Okay. And then now, oh, we forgot mass. So now we put in vehicle mass. And unsprung weight. Oh. It's case sensitive. Okay. So you can see response curves of your suspension components. This is let's see, where is the one that we want? So you can see that while your wheel can move a lot, your body won't move that much, and you can evaluate design decisions based on the output of these plots. By changing your parameters in MATLAB, you can view different response characteristics by changing, let's say, the spring rate of our of one of our springs. We can buy either a stiffer tire or a stiffer spring and then rerun the simulation to see what that does. We can see that it moves the early response down a bit, but it still causes steady state oscillations. So you can damp those So we might say, okay, we want to now have higher damping ratios. So simply increase the damping coefficient, rerun the simulation. This allows you to evaluate design decisions without having to without having to buy and test different components or have detailed CAD models, run FEA simulations, flow simulations, etc. Simply take the model that you have that's generated by math, simulate it. You don't have to write down the math, but you just have to solve it. So the way that you can create a simple F equals MA simulation, which is what this is effectively, is so you want a sum block, and instead of just two components, you want to have as many forces as you have on your, as many forces as you expect to have on that component. So in this case, we have our damping force, our spring force, and that's it. We're ignoring gravity for the fact that we expect the loads caused by inertia and movement of the body to be greater, as well as the fact that at steady state, when you have a spring, when you have a mass under a spring, the spring will depress itself, and and the equilibrium position of the spring accounts for gravity. So we're going to model about the equilibrium point. So we just simply take our 4 blocks. You can change the icon shape to be rectangular if you see that it suits your needs a bit more. Now now you have your forces, right? And you're going to take a gain block and you're going to scale by 1 over the mass of whatever you're trying to simulate. Simply take that. Now, once you have the mass, you have your acceleration, right? To get velocity from acceleration, use an integrator block. And now, anything on this output here is your velocity. So now, to get position from velocity, simply use another integrator block. So there's a trade-off with doing it this way. So when you have a second-order integration being done numerically using 2 first-order integrator blocks, you will have accumulated error. A good example of this is if you're trying to model a bouncing ball. So if you have a damping coefficient on your bouncing ball and you simply use these two integrator blocks one after another, and simply have them bounce, you're going to see that it never actually stops bouncing because of the error inherent in the integrator blocks, because they add up and gain to each other. However, there is a workaround for this called the second order integrator block. The second order integrator block allows you to integrate 2 times in one block. This avoids the issue with the two first order integrators. However, you cannot get the velocity data from this block. It's internal to the block and cannot be probed. So if you had viscous damping, which is dependent on your velocity, you would not be able to pull that from your second order integrator. However, if you simply need acceleration and position, or if you know acceleration and you need to know position, simply use the second order integrator block. However, in this case, we need to identify damping. So what we have here on this output is position. So for a spring mass system, we're going to have another gain block. So we're going to say K1. And to flip a block, simply right click on it and flip the block so that it points in the right direction, because we're going to add feedback using this. So going out K1, simply add it back, and then do another gain block and do D1, flip it. All right. And then you have your 2 forces acting on the system for a single mass. So now if you had a second one of these and you took different parts of it and added it back into the system, you would create the suspension model we have. As you can see in this, we have this block is effectively the same. We have a sum block, a gain by 1 over mass to get our acceleration, which we integrate, and after which we get our after which we integrate again and we get our position. Now we have the interactions added in to create the dynamic model. So as you can see, that when we get to our velocity here, we're subtracting from it the relative speed of the road surface moving up, and at the position, we're also subtracting the relative position of the road surface to the tire. Now, what this allows us to do is that we have our input. We're accounting for the input and its derivative in the system, and from that, we are seeing the dynamic events follow from our scope. We can then see up here, we have our mass, our spring mass system for the vehicle itself. We divide by its mass, and we integrate it, get its velocity, integrate it again, get its position, and then we connect the two using the damper and spring, and show it using relative positions and such to calculate the damping forces acting on each component. As you can see, this is a very mathy process, and a lot of people will not be doing it this way. So that's why Simulink has something a little bit easier. But this one makes a lot more sense. This is a model of a electromechanical system. What it has is you start out with a DC voltage source. You have your PWM voltage that you want, an H bridge for your motor, current sensor, DC motor, electrical reference. We'll get to the solver configuration, and then you have your mechanical side, which you say, okay, I have a gearbox, a rotational damper, and some inertia. With this, you've effectively modeled a very complicated system that if you tried writing all the differential equations out would take you probably a couple of hours to do. This is something that I'd imagine to see on a system dynamics test. But you can quickly model this sort of system using Simulink without having to account for all of the interactions between the electrical and the mechanical side. But here's the thing. You can't just attach a scope directly to an electrical connection. And you can't directly attach a scope to a mechanical connection. You have to use a Simulink converter. Using the Simulink converter, you can then output to a scope, and you can see your current usage, as well as if you wanted to add other blocks, you can look at the rest of it. Some things that you want to look at with this system. So right now we have a 5-volt supply attached to a 30 ohm motor. So what we're going to do now is we want to see how fast that can turn a inertia that has 10 kilogram meter squared moment of inertia. So to see how fast it's turning, we have to first convert the angular motion into a ideal rotational motion sensor. Initial angle is 0. So you have this rotational motion sensor block now, which you found by just searching for it. Connect it up. And then simply take a scope. And yeah, you can't connect it. So you have to use one of these guys to convert what you need into what you want. And you can see that it quickly gets up to a top speed, but there is a transient which you can see getting up to about 3,500 RPM. And from that, you have your simulation. Now you can add other things, such as, let's say you wanted to have a ramp up on the DC motor side. You can replace that with a voltage source. Or not. So your voltage source can be modified to include capabilities such as noise. And you can see that what noise in your power line has an effect on your DC motor. However, you can also see that by adding noise and other components to your simulation, you increase its runtime significantly. Your 10-second simulation just took about 15 seconds by just adding that noise component. Now let's just say something that you may have realized is that these simulations only run for 10 seconds. For modeling a rocket, you might not want that. So what you're going to change that, you go to your model configuration, change your start and stop time. You might think that this is, you want to go just to 100 seconds, apply, and then you click OK, run it. I don't know if this one particularly will show it. So you see that your transient just went all the way gone because you increased your time scale up to 100, but you can't zoom in and see it that well. What happened is that your resolution also went down. So although Simulink will run your simulation longer, it'll default to a step size of a relative tolerance of 1 to the 10 negative third, and sometimes the max step size messes up and you won't actually get you'll get a very large step size, like a second or two, which causes an accumulation of error. So simply you can set a maximum bound of your step size to be 0.01, apply it, click OK, and then you can run your simulation again. However, again, keep in mind that the more you do that, the longer your simulation will take to run, and you will probably be sitting there for a little bit more time waiting for it to post-process your results. Also, don't plan on using your computer too much when it's trying to run the simulation. All right, let's see. Well, that's it. Mostly. Any questions?
Cool. So this is a best case type tool for modeling dynamic systems.
Yeah, so depends on exactly what type of dynamical system. So there is something called the 2DOF block, or well, 3DOF. Yeah. So 3DOF, rotational dynamic modeling. But here's the thing: you can't just connect these blocks to this block. You have to connect the output of a Simulink block to this, and it'll do the I alpha thing for you. Because you'll give your initial velocity, your initial position, your mass, and here's the thing: it won't actually give you inertia. So you won't put in an inertia tensor for 3DOF. There's also something called 6DOF. 6DOF. And this thing will give you put in your inertia tensor, and it'll solve the dynamics for you. Anything that requires you calculate your forces. This is effectively the same thing as, where is it? This. It's literally just doing the same thing that we did with 2 integrator blocks. Well, it's actually just doing this part, giving you your accelerations in each direction. You have to integrate and then do all of this to get your forces. And it'll give it to you for every time step. So it'll give you its velocity at every time step, its it'll. Let me rephrase this. I messed up my English. So, it'll integrate for you, but it'll integrate at every time step. So, its outputs are going to be the same as the outputs of our block, of our integrator blocks. You just have to choose what to do with them. So it's like our Python script that we have. It'll do that same math for you. Yeah. And then there's 3 different. So I only talked about 2 packages here. There is also a Thermodynamics package. So let's see. Simscape, fluids, thermal liquid. You can have tanks. So let's say you have your tanks and accumulators, you have a tank. You can model in orange all your tank properties. You can run a thermodynamic simulation with this. There's also valves and other fittings. It's not as rich as your mechanical side, but it'll have everything that you'd see in a first-year thermo course, like compressors, heat exchangers, stuff like that. It'll model transient as well as steady state stuff. So if you want to run like quick analysis of like a circuit using different properties, you could do that, and you could see that sort of thing.
I have to look into that. We could do some feed system transient modeling to confirm our experimental data.
Yep.
But so this is good for hydraulic and mechanical systems, but mostly mechanical systems.
It'll actually, and the other thing is that you can combine all of these together too. So if you have a compressor, a turbine. If you have a turbine, its output will be green, so you can connect up mechanical stuff to the output of a turbine. And then you can also build up entire things. And then something I didn't show was that you could make a subsystem. Let's say I want to turn all of this into a subsystem.
So you can turn it into a block.
Yep, you can like compress it all into one block, and then you can see.
Go in, and like you can open that in a separate window then.
Yep. Currently, Flight Dynamics is set up. Let me show you. And then, where is it? K1 Flight? No. K1 Flight Dynamics. And then Simulink. Our models are aerodynamic controls, DEFBODs, environmental, and propulsion. Each of those will be blocks in the high-level model, which isn't there yet. Yeah, here it is. The high-level model is there. They're all going to be sub-blocks in the high-level model, which will connect up to each other using those lines and plots and everything. Generate data.
What kind of inputs would, say, a valve function have?
Let's see. So, valve. So, 2-position valve actuator. So, there are a lot of valves, and I'm not quite sure. However, here's the thing. A lot of my work when I'm doing Simulink, it's done through like Simulink valve, and they'll actually explain everything. They'll explain their modeling, their assumptions, and everything that they've used to design that component. So if you have, let's say, a ball valve that you need, it'll show you how they came up with all of the models that they're using in it, and it'll tell you, okay, here's what you're going to have to give us, and here's what you're getting out, and here's the assumptions we made to get that.
Very cool.
Yeah.
Because I saw that they wanted effectively discharge coefficient, flow area, and whatnot.
Yep. They will take it'll take a lot of information sometimes, but then there's also simplified models of mostly everything. Like the gearbox doesn't account for inertia. So what you do is you can add inertia to the output of your gearbox related to what your gearbox inertia should be. And that's effectively just your standard gearbox inertia calculation. And then you can model that as well as other stuff. And then you can also connect these up in any order you want. You can also have feedback into the system where you can get your output of your mechanical is then put back in as work into a fluid system, which is used to convert energy, etc. And you can get a cycle and stuff, model the cycle. You can get PV diagrams out of this, whatever you want.
Very cool. I'm intrigued by the fluid sim.
Yep. Fluid simulation is something I'm trying to do. And also, if you look at that textbook over there, right behind it, it's by Koshiro Ogata. He will go over some things. He won't use Simulink. What he'll use is he'll use he'll use math. However, to solve everything, he'll use MATLAB. Everything you can do with the black lines, you can do with straight MATLAB code. So what you can do is that if you have a transfer function, there's something called like a transfer function block. And simply type in the numerator coefficients of S, the denominator coefficients, and it'll give you your transfer function, which you can then say, okay, here's the transfer function. You pass in your input and stuff, and you have your output. He will do it using like state space equations and a solver in MATLAB. Mm. And later on in the textbook, he has a lot of fluid examples and thermo examples about balanced flow and stuff like that. We'll model the transient operation of a lot of thermal systems in pretty detail. Another resource that I've been trying to get my hands on, but it's kind of expensive, is System Dynamics. And then let's see, what is this? Yes, this Thermodynamics textbook is apparently one of the best system dynamics textbooks that you can get your hands on. It will it'll teach you how to do modeling of interdisciplinary systems very specifically, as in, let's say you have motor connected to mechanical system connected to fluid system, which creates electricity and which modulates your motor. Now, you try modeling that yourself with no knowledge, you're going to spend days doing it. This book teaches you how to do it. So it's very useful for the systems engineer. This textbook and then Modern Control Engineering by the same author of that textbook by Ogata. I've shown that to Neil. It's in the Flight Dynamics textbook. Very useful texts. Teach you control systems and stuff. Lots of math. Lots and lots of math. A lot more than would keep people interested for 2 hours. But if you know differential equations, you can do system dynamics pretty well.